Hello all. Hello all. So I wanted to do a quick sort of demo video here walking you through kind of how I would go about using Sympy to sort of go through a Lagrangian type problem. Because some of these sometimes have a lot of sort of algebra or small steps that you kind of have to go through as you're doing them. And sometimes it's easy to make mistakes when you're doing that. So at the very least, sometimes I'll go back and use Sympy as a sort of way to check myself at the end to make sure that I actually came up with the correct equations of motion. So I thought we would look at here is just sort of the example we did from class, which is our sort of classic Atwood machine in this case. And we saw in that situation that, so this is going to be a pretty simple example, but it's going to walk you sort of through how I would go about doing this. And we saw that since we have one constraint, we can write everything in terms of sort of just one of our variables when we're going through this. So I'll refer back to this sort of occasionally when we're going through just to make sure that we're remembering what's going on. So if I was starting out from scratch here, I would go ahead and I got to import all my usual suspects. So we're going to want to make a plot at the end. So we'll do matplotlib inline import matplotlib.pyplot as plt. And I'll set my style as well, so plt.style.use born dark grid. If I'm going to be plotting things numerically, I'm going to want numpy as well, so import numpy as np. And then, of course, most of this I'm going to be doing with Sympy symbolically, so I need Sympy as well. So import Sympy as sim. Normally here I would go ahead and do sim.init printing to make everything look nice. But something that I particularly like to do when I'm doing Lagrangian type problems is we're used to always using like x dots or y dots to be our time derivatives. And by default, Sympy will write out the whole like dx dt, which makes the equations end up looking a lot clunkier. There is a way though that we can kind of convince it to display those time derivatives as in dot notation. And it's actually because there's sort of a sub-library of Sympy that is based off of mechanics. So to get that sort of printing, what we can do instead is we can do a import sympy.physics.mechanics as mech, and then I'll do mech.init, and it's v printing instead. And if we run that, hopefully we don't get any errors. Sweet. So at this point, we're set to sort of start putting together the skeleton of our Lagrangian problem. And for any Lagrangian problem that you're starting out, you want to know what's the kinetic energy, what's the potential energy, so that you can put those together to create your Lagrangian. And of course, those kinetics and potential energies are going to be some sort of function of the parameters that we have in our system. So in this case, we have sort of a few things that we would be taking care of that I'm going to probably want to go ahead and call constants initially. One of which is we have some radius of the pulley. That's going to be some capital R constant. And that's going to be symbols. I'm going to make sure that that's positive, just to be clear. We also have time symbols, which I'm going to let be either direction. I mean, technically speaking, we'd normally have it running forwards, but technically the physics is time invariant here. So, and then our masses. Those are also going to be positive, so we'll add those up here. I'm just going to say M1, M2. And note, when you write them out this way, this is what sort of the code, how you would refer to them in the code, and this is how they would show up in your expressions when they get printed out. So what I'm going to do here is actually I'm going to do M sub 1 and M sub 2, so that when they get printed out, they have like nice subscripts attached to them, just because it makes it easier for me to read these sorts of things. And I think that's all the constants. I guess we're also going to have gravity playing a role in here, so we'll also tag it in here as well. And all those things can be positive. That seems totally fine. There is, of course, one other main thing that we're going to be dealing with a whole bunch, which is our actual x and y positions here. So we had our x and y positions that we're defining everything in terms of. And both of those are going to be functions of t, and we're going to take advantage of the constraint so that we will write y basically as a function of x in this case. So if we want to directly refer that something is going to be a function of t, the way we can normally do it is we, instead of calling it a symbol, we'll call it a function. I still want it to look like x, and then here I will say directly that it is going to be a function of t. Note, I have to have defined t as a symbol up above in order for this to work properly. And then, of course, for y, if y was just the generic function of t, I could do the exact same thing. But in this case, y is our whole, it's related to x. So we're going to say minus x of t, and then it was plus that constant, which is going to be, our length of our string. And minus pi r. And hopefully, if we then display these at the end, we will get that x is not callable. Yeah. So if I look at what x is, it's just going to be some function of x. If I look at what y is, it's going to be minus x plus that weird constant that we had going on. And now we can actually start going about putting together our various energies. So the first part, let's just add in a quick. So these are constants. And then let's make these our defining energies. All right, so in terms of defining our energies, we got our kinetic and our potential that we need to account for. So our kinetic is just going to be our good old tried and true 1/2 mv squared for both masses in this case, so x and y. If it hasn't come up with you before, you'll notice that if you write in 1/2 into Sympy like this, what will inevitably happen is Python converts the 1/2 to 0.5, and then Sympy tries to treat it as a decimal throughout the rest of the process. To avoid that, what you can do is you can do sim.rational 1,2, which is basically telling Sympy, hey, this is an integer 1 over an integer 2. Don't try to make it a decimal. These are integers. So we got a 1/2 times our m1 times, and m1 corresponded to x over here, and m2 corresponded to y. So we got m1 times x. But it's not x, it's derivative of x, because it's the velocity of x. So x dot diff with respect to t squared, and then plus the other one. So sim dot rational 1,2 times m2 times y dot diff t squared. And we can go ahead and look at that to make sure it's looking okay. And you'll note it prints them with the dots in there, as we would have expected, and it also goes ahead and, our y was technically in terms of x. And of course, those constants don't matter when we have taken the derivative. And if we do this, it'll probably even lump things together for us, so we can see it that way. For the potential energy, of course, we just have our h's, or mgh's. So for the first, we'll have an m1 times g times its height, which is just x, plus an m2 times g times its height, which is y. And if we print those out as well, we got those terms. Again, just in terms of our x's. So therefore, our Lagrangian is just going to be, I shouldn't have called this logger, is just going to be t minus u. Is going to give us sort of that whole mess, which is what we would have gotten and what we did get doing it by hand all the same. So from here, then it's just a question of putting together our sort of various Lagrangian equations to compile our answer. So to do that, we just need to remember that our equations. So for our Lagrange equations, we have the partial of the Lagrangian with respect to just the constant equals d dt of partial of the Lagrangian with respect to x dot in this particular case. So I'm just going to call this the right-hand side of the equation. So that's just going to be the partial Lagrangian with respect to the constant, which is x. And our left-hand side is going to, well, at least d dt of the left-hand side, is going to be our Lagrangian with respect to, now we're taking the derivative here with respect to x dot, so we need to be careful that we actually say x dot diff t, because that's what x dot actually is. So we want to take the derivative with respect to x dot, and then of course it's d dt of that, so once we get that whole thing taken care of, we want to go ahead and take the derivative of that with respect to t. And we would expect to get some sort of double derivatives out in the end, and so that is what we're getting out in this particular case. That's what we've got in class as well. So then, of course, if you wanted to solve, like to get your equations of motion just in terms of, say, the constant, or your x double dot in this case, then we can just, paste the pieces together and use sim.solve. In this case, it would be very easy to do by yourself, but for more complicated cases, this can be very useful to put together. So I can either bring everything onto one side and make it equal to 0, or I can use sim.equation and put in my various pieces. So I'll have my right-hand side and my left-hand side. So that's just saying, hey, the equation is right-hand side equals left-hand side. And then what do I want to solve for? Well, I want to solve for x double dot. So that's x dot diff t2, because it's two derivatives with respect to t when it's going through. And if we run that, we get spit out this term, which should look really familiar because that's the same acceleration term that we got in class last time. Here, I'm going to go ahead and just call this, Excel, sim.solve. And there's only one solution there, so I'm just going to grab that first one. So we got something that looks like that, or a nice constant acceleration. And from this point, we could just go ahead and, if all you wanted was the equation of motion, you could stop here. If you wanted to sort of go farther, in this case, this is just a constant. So if we wanted to figure out what the velocity is, we could just take one time derivative, or time integral with respect to this. If we wanted to know what the sort of position at any point in time was, we just take two time derivatives, or two time integrals with respect to this. So in this case, it's easy to do it constantly. Maybe it's something more complicated, and you can't solve it analytically in this case. Well, in that case, you could basically take your acceleration, substitute known values of m1, m2, and g into it, lambdify it to make it into an actual sort of NumPy Python function, and then you could use that in your normal ODE int numerical solutions to sort of plot out the path numerically in that sense. But this is frequently how I will sort of go through checking myself, especially if sort of some of the math got pretty hairy. Because in this sort of problem, these steps are sort of very easy and straightforward. But in many of the Lagrangian problems we're looking at, there's like a lot more terms going on, so things get a little bit more hairy. So this is just kind of my process that I can, at the very least, check my equations of motion to make sure everything went okay in the end. And that's it. Thanks.